Welcome to Sleepless Scientist, the channel where science isn't just fascinating. It's also a gentle companion for your restless nights. Whether you're seeking relaxation, peaceful knowledge, or just something to lull your busy brain, you're in the right place. Tonight, we dive deep beneath your feet, all the way to the heart of our planet, to ask one simple but world-shaking question: what happens if Earth's core stops spinning? Thank you for joining me on this strange but thrilling adventure to the center of the Earth, and I apologize in advance if this keeps you up rather than puts you to sleep. But if you find yourself intrigued, bewildered, or oddly soothed by the idea of Earth's engine grinding to a halt, please like, subscribe, and comment where you're watching from, maybe the time of day too. Now, let's journey down through the crust, beyond the mantle, into the molten mystery of the core. The Earth, though it may seem firm and still beneath our feet, is far from a frozen, lifeless rock. Beneath our cities, forests, deserts, and oceans lies a structure so dynamic, so temperamental, that it can literally shape the world above. The inner Earth is not a single mass, but a layered orchestra. The crust, the lithosphere, is the skin. The mantle beneath it is a thick, churning sea of solid rock that flows sluggishly over geological epochs. And below all that, at a depth of about 2,900 kilometers, begins the outer core, a river of molten iron and nickel, swirling at temperatures reaching over 4,000 degrees Celsius. Deeper still, past that metallic inferno, lies the solid inner core, roughly the size of the moon, but much denser. This core, both inner and outer, is not just a passive ball of metal. Spins. Not only does it rotate, but it may rotate slightly faster or slower than the planet's surface. This spinning action is believed to generate Earth's magnetic field through a process called the geodynamo, where the movement of electrically conductive molten metals produces a global magnetic force. Without that field, we would be in trouble. A lot of trouble. Earth's magnetic field is our shield, an invisible guardian that stretches far into space, deflecting charged particles from the sun, deflecting solar wind, and helping to prevent our atmosphere from being slowly stripped away. This isn't science fiction. Mars, a once dynamic world, seems to have lost much of its magnetic field billions of years ago. With it went much of its atmosphere. Today, Mars is dry, barren, and exposed. Earth, on the other hand, is protected thanks to the dynamic spinning within its core. Now imagine what might happen if that engine, this molten dynamo, stopped turning. Stopping the Earth's core isn't just a hypothetical exercise in science fiction. It is a terrifying thought experiment that forces us to rethink what holds our planet together. Let's start with one of the most immediate consequences. If the spinning core stops, the geodynamo stops. No more magnetic field. Within days or weeks, satellites in orbit would begin to fail as cosmic radiation floods their circuitry. The GPS you use to find your favorite coffee shop might give you directions to the nearest black hole instead. But the loss of the magnetic field isn't just an inconvenience for electronics. Without it, Earth would become vulnerable to solar storms. These are powerful eruptions of energy and particles from the sun that can disrupt power grids, knock out communication systems, and, in extreme cases, fry unprotected electronics on the surface. A strong geomagnetic storm in 1859, known as the Carrington Event, sent telegraph systems into chaos. Back then, people saw auroras as far south as the Caribbean. If the same event occurred today with no magnetic field to deflect the storm, the global consequences would be catastrophic. Satellites would burn out, navigation systems would collapse, and high-altitude flights would expose passengers to dangerous radiation doses. Life on Earth might not vanish overnight, but the environmental pressures would begin to mount. The magnetic field also helps guide migratory animals, birds, turtles, whales. Even some insects use Earth's magnetism to navigate. Without it, millions of animals would become lost, crashing migrations that have existed for eons. The chaos wouldn't be restricted to the animal kingdom. Our own health might take a hit. Increased radiation from space could raise rates of cancer, especially skin cancer, as cosmic rays and solar particles begin to filter through what used to be a well-fortified atmosphere. Now consider climate. While the core spin doesn't directly drive weather patterns, there is some interplay. The magnetic field helps retain our atmosphere, and with it, the pressure and composition necessary for stable climate systems. Without it, we might slowly begin to lose some of that atmosphere. It would not be like opening a vacuum tube and watching the air rush out, but a slow, agonizing escape over centuries. Molecule by molecule, the atmosphere could be stripped by solar winds, especially lighter elements like hydrogen. Oxygen would follow. Eventually, Earth might resemble Venus, scorching and toxic, or Mars, cold and barren. Beneath the surface, the core spin is also tied to convection in the outer core. If the spinning stops, this convection, the cycling of hot and cooler material that keeps the outer core in motion, could begin to stagnate. That could, in turn, affect the mantle. With less energy transferred upward, the mantle might cool slightly, altering tectonic activity. Earth's tectonic plates, which create mountains, earthquakes, volcanoes, and new seafloor, are part of a grand conveyor system powered in part by heat from the core. A stagnant core could mean less tectonic motion. Earthquakes might become rarer, yes, but so would volcanic activity. That might sound good until you realize that volcanoes are a vital part of Earth's carbon cycle. Without them, the planet could slowly lose its ability to regulate carbon dioxide and temperature, leading to long-term climate instability. The exact timeline of these changes is uncertain. Some effects would be nearly immediate. Satellites. Failing, increased radiation, magnetic compass errors. Others would unfold over centuries or millennia, the slow erosion of our atmosphere. The gradual shift of climate patterns, the breakdown of natural cycles. But perhaps most haunting is the psychological impact. Humans have always lived under the protective umbrella of Earth's magnetosphere. From our earliest ancestors watching the northern lights to modern astronomers mapping solar winds, we've lived with this invisible force. If it suddenly vanished, the world would not only be more dangerous, it would feel more alien. Is there any precedent for such an event? Interestingly, the Earth's magnetic field has weakened in the past, and it even flips every few 100,000 years. North becomes south, and vice versa. These flips can take thousands of years and are not associated with mass extinctions, suggesting that a weakened or shifting magnetic field is survivable. But stopping the core altogether is a different matter. It's not just a shift in polarity. It's a shutdown of the engine. Could the core actually stop spinning? Scientists think it's incredibly unlikely. The rotation of the core is sustained by the overall momentum of the Earth and heat from radioactive decay. But the core doesn't spin in perfect sync with the rest of the planet. Some studies have suggested that it slows down or speeds up slightly over time. And there's even speculation that its rotation direction may reverse in some way relative to the surface, but this is more a matter of relativity than actual backward spinning. Still, if somehow a cosmic wrench were thrown into the works and the core did truly stop, the world would be forever changed. It would be as if the heart of the planet stopped beating. No longer would our world have its invisible magnetic pulse. No longer would it be protected from the fury of the cosmos. A spinning core is not a luxury. It's a necessity. So the next time your compass needle twitches or you see an aurora dancing across the sky, remember that far beneath your feet, a river of metal is churning and spinning, keeping our planet alive, magnetic, and wonderfully habitable. The Earth's core is not just the center of our planet. It is the engine of everything that lives above it. As the heartbeat of the planet begins to slow in our hypothetical scenario, Earth as we know it enters a new and uncertain chapter. The initial panic may be technological, satellites going dark, aviation systems misfiring, compasses becoming mere decorative relics, but the deeper changes happen slowly, imperceptibly at first. But with far-reaching implications, humanity would find itself living in a world increasingly untethered from its invisible magnetic guardian. The solar wind, an ever-present stream of high-energy particles emitted from the sun, once deflected like raindrops off an umbrella, now starts to scratch away at the atmosphere like a cosmic sandblaster. The first layers to feel this effect would be the exosphere and thermosphere, the most fragile and outer parts of our atmospheric blanket. This is where satellites orbit and where molecules begin to thin into the vacuum of space. These layers are normally inflated by solar radiation, puffed up like a balloon, but protected from the worst effects by the magnetic field. Without that protection, we'd start to see an atmospheric thinning, and over decades and centuries, gases that should be safely held within Earth's gravity could be stripped away. The planet wouldn't lose its air overnight. Our atmosphere is stubborn and heavy, but the leak would begin, one molecule at a time. Driven by solar fury and unchecked by magnetic resistance, on the ground, life would begin to notice. Not all at once and not everywhere, but migratory animals that depend on geomagnetic cues would struggle first. Turtles might hatch and swim in the wrong direction. Birds that fly across oceans could end up exhausted and stranded. Even certain bacteria, which align themselves to magnetic fields, would become confused. This cascade of biological misdirection would ripple through ecosystems. Predators that rely on the predictable patterns of prey migrations would be left hungry. Insect populations might explode in areas where their natural predators are now out of place. The quiet, invisible forces that help regulate the rhythms of life would go haywire. In human life, there would be consequences, not just in technology, but also in health. The magnetic field deflects a significant portion of cosmic radiation. With it gone, high-altitude regions and flights would become risk zones. Passengers on transpolar flights might receive doses of radiation high enough to affect health. And flight routes would need rerouting to lower latitudes, increasing costs and travel time. Airports near the poles could lose relevance entirely, as flights avoid the regions where exposure is greatest. People living at higher elevations might find themselves advised to stay indoors during solar storms, just as we take shelter from hurricanes or heat waves today. Meanwhile, auroras would become more frequent and widespread, an eerie and beautiful byproduct of a worsening situation. With more solar particles reaching the upper atmosphere, charged collisions with gases would ignite colors in the sky, not just near the poles, but possibly across most of the planet. These lights would dance across equatorial skies, offering awe-inspiring views while quietly signaling a breakdown of natural defenses. The northern lights in New York, or the southern lights in Nairobi, might become a normal part of the evening, but their appearance would be less a gift and more a warning. Scientists would rush to model the new radiation environment. Solar storms would become threats, not just to astronauts or satellites, but to agriculture. Solar particles can increase mutation rates in crops, potentially lowering yields or altering growth patterns. Farmers might have to adopt new shielding technologies or switch to hardier species. Meanwhile, cancer researchers would notice an uptick in radiation-linked cases, particularly among children and people living in regions with weak atmospheric density. The medical world would scramble to respond to the quiet escalation in DNA damage caused by the unfiltered gaze of the sun. Below the surface, tectonic processes would begin to slow. The core's movement plays a role in driving convection currents in the mantle, which in turn power plate tectonics. With less rotational Momentum and less energy being distributed through the mantle, the movement of tectonic plates could become sluggish. Mountain building processes might grind to a halt. Subduction zones, where one tectonic plate slides beneath another, could stall. Volcanic activity might decline as less heat is transferred upward. This would mean fewer eruptions, fewer earthquakes, and potentially more stable landmasses. But that stability comes with a price. Volcanoes do more than just destroy. They create. They release gases that help regulate the atmosphere, including carbon dioxide, which is essential to maintaining a greenhouse effect and keeping Earth warm. If volcanic activity wanes, the carbon cycle slows. Over centuries, this could cause temperatures to drop. Glaciation might return, especially if combined with a slight dimming of the sun or changes in Earth's orbit. The irony is rich. Well, the lack of a magnetic field exposes us to intense solar radiation. The reduced volcanic carbon emissions might send us into a deep freeze. The oceans, too, would feel the slow march of change. Ocean currents are affected by the Coriolis effect, which is influenced by Earth's rotation. A still core wouldn't stop the rotation of the whole planet, but shifts in internal dynamics might alter the way heat is transferred through the oceans. Thermaline circulation, the global conveyor belt of warm and cold currents, could weaken or shift. This would affect regional climates. Europe might cool dramatically, while equatorial regions could become even hotter. Fisheries would collapse in some areas and bloom in others, further destabilizing food supplies. All of this happens while Earth's crust continues to sit upon a cooling, quieting mantle. Without the churning motion of the outer core, the magnetic field doesn't just stop, it disappears. The outer layers of Earth become a silent battleground between solar particles and atmospheric molecules. Satellite engineers and climatologists might collaborate to build artificial magnetospheres for Earth, massive orbiting loops of current or magnetic shields powered by solar energy. But these would be ambitious projects requiring enormous resources and international cooperation. And then, of course, there's the human reaction. People would begin to ask if Earth is dying. News outlets would alternate between panic and dismissal. Conspiracy theories would sprout. Some would believe the world is ending. Others would argue it's just a cycle. Meanwhile, scientists would scramble to understand the physics behind the stoppage. Did some external force cause the core to halt? Was it a buildup of pressure? A loss of momentum? An unknown interaction with deep space phenomena? Or was it simply a rare and catastrophic natural event written into the planet's fate since its fiery birth 4.5 billion years ago? Despite the growing chaos, the surface might still look serene in many places. Forests would remain green. Rivers would flow. Mountains would stand quiet. The skies would sparkle with auroras. But underneath, the Earth would be changing, growing, colder, more fragile, less shielded. And slowly, life would adapt. As it always does, new species would evolve to tolerate higher radiation. Human civilizations might migrate underground or to magnetic domes, protected by artificial shielding. Cities could be redesigned to incorporate layers of lead or polymer insulation against the storm of cosmic particles. Ironically, might become safer since we'd already be preparing for the conditions of deep space right here on Earth. Geological time doesn't care about human schedules. The effects of the core stopping might take millennia to reach their full crescendo. But once the process starts, it's hard to reverse. Restarting the core, if such a thing were even imaginable, would require injecting energy on a scale that dwarfs all human capability. It would be like trying to jumpstart a star with a car battery. More likely, humanity would adapt. We are, if nothing else, problem solvers. Curious, tenacious, and slightly reckless. As our magnetic shield fades and the solar wind begins its slow assault, we would enter a new geological era. Call it the demagnetocene, perhaps. A time when the planet that once bristled with magnetic life becomes quieter, colder, and a little more exposed. But also, perhaps, more united in its efforts to understand, adapt, and endure. Beneath our feet, the spinning stops. Above us, the stars shine a little brighter through a thinner, more dangerous sky. And somewhere in between, we go on living. Inventing, adjusting, surviving under the faint. Fading memory of a magnetic Earth. The silence beneath Earth's surface, where once molten metals swirled with unimaginable heat and velocity, now becomes the dominant state. With the dynamo stilled, the internal engine of our planet has entered a phase of cosmic dormancy. It is not death, but something colder, a planetary slumber where motion no longer feeds magnetic breath. And above this sleeping core, the atmosphere and all life within it begin adjusting to an increasingly unfamiliar planet. As the magnetic field continues its disappearance, certain effects grow more pronounced. For example, ozone depletion would no longer be a distant ecological concern. While the ozone layer protects us from ultraviolet radiation, it is stabilized, in part by the magnetic field that shields it from energetic particles. With that defense gone, UV radiation from the sun bombards the stratosphere more directly. Ozone molecules, already fragile and sensitive to pollution, begin to break apart more easily under this increased bombardment. The thinning of the ozone layer would have significant implications for life. Skin cancer rates would rise globally. Plants, particularly those in tropical and high-altitude ecosystems, would suffer DNA damage. Photosynthesis could be inhibited, causing agricultural yields to decline. The food web would begin to wobble. Oceanic phytoplankton, the base of the marine food chain and a major oxygen producer, are sensitive to ultraviolet light. If their numbers drop, the ripple would extend from krill to whales, and from coastal fishing villages to global seafood markets. This ecological strain is accompanied by strange new weather patterns. As ocean currents slowly destabilize due to altered rotation dynamics and uneven solar heating, wind systems begin to shift in unpredictable ways. The trade winds that normally cradle the equator may falter or shift latitude. Jet streams that normally swirl across continents in reliable bands could meander unpredictably. Regions long accustomed to rain find themselves locked in drought. Others, once arid, suffer flooding. Even without the core spin, Earth continues to rotate on its axis. Day and night still alternate. Gravity still holds. But the internal gyroscope, the spinning molten mass that adds subtle balance to the planet's wobble, is no longer operating. Earth's axial precession, the slow conical motion that changes. The orientation of our tilt over tens of thousands of years might begin to behave erratically. Climate cycles tied to this wobble could shift, triggering glaciations or warming periods out of sync with historical patterns. Civilizations built around seasonal predictability begin to adapt to a world of strange summers and uncertain winters. Agriculture becomes less reliable. Crop failures increase. Governments pour resources into vertical farming and genetic modification of plants resistant to UV and radiation. Still, food becomes scarcer, and hunger grows in places long protected by climate stability. Coastal cities, once the hubs of global commerce, begin to face another creeping crisis: atmospheric escape. The exosphere, the highest layer of our atmosphere, is the last tenuous connection Earth has with space. It is here that atoms and molecules energized by solar radiation and no longer trapped by magnetic lines can reach escape velocity and drift into space. The slow but continuous loss of hydrogen, helium, and eventually heavier elements means that Earth's atmosphere begins to thin, not catastrophically, but relentlessly. Air pressure begins to drop over millennia. Breathing at high altitudes becomes more difficult. Entire towns relocate from mountain ranges to lower elevations. Airline industries, already burdened by the rerouting of flights to avoid radiation belts, must now contend with changing lift dynamics as air density declines. Planes require longer runways, stronger engines, and higher fuel consumption. New forms of propulsion are researched. Suborbital flights become more appealing, not for speed, but for safety above the thinning, chaotic sky. Meanwhile, the energy sector must evolve rapidly. Solar flares, once deflected by our magnetic shield, now make direct contact with power grids. Massive transformers fry in spectacular bursts. Blackouts become common during solar maximums, especially in regions at higher latitudes. Engineers work to decentralize power systems. Microgrids and solar backup networks become standard. New forms of radiation-hardened infrastructure are deployed, but the cost is enormous. Nations must divert budgets away from traditional development to planetary resilience. In more optimistic corners of science, there are efforts to artificially regenerate the magnetic field. Giant superconducting rings are proposed, kilometers wide, buried deep underground, or launched into orbit. These structures aim to simulate the geomagnetic field through controlled currents. But such projects remain theoretical, expensive, and decades from deployment. In the meantime, space agencies increase funding for planetary monitoring, hoping to detect early signs of more extreme shifts in Earth's behavior. Through all this, the deep Earth cools. The core cessation in motion has implications beyond magnetism. T is a heat engine, after all. With less movement, less energy is transferred into the mantle. The mantle cools slightly, causing it to contract. That contraction adds strain to the crust, which begins to fracture in unexpected places. Old faults long thought dormant awaken with creaks and groans. Earthquakes appear in regions with no history of seismic activity. These are not always catastrophic. Many are small, shallow, and isolated, but they disrupt infrastructure and sow confusion. Meanwhile, with volcanic activity slowing, the carbon cycle continues to falter. The atmosphere, already thinned by solar stripping, now also begins to lose carbon dioxide. Over millennia, global temperatures decline. This cooling is not dramatic like a nuclear winter. It is subtle, progressive, and insidious. Each century becomes slightly colder. Glaciers grow. Sea levels begin to recede slowly. Coastal cities, which had once prepared for flooding, now face expanding shorelines. Harbors dry. Fish move further offshore. Infrastructure built around a once warm ocean begins to crumble. Culturally, humanity begins to mythologize the event. The silent core becomes the stuff of poetry and cautionary tale. Artists depict a world with auroras overhead and strange silences below. The northern and southern lights, once limited to high latitudes, now adorn the skies of equatorial cities, becoming both natural marvel and ominous reminder of Earth's changed state. Some cultures interpret them as celestial warnings. Others as the Earth's sorrowful song. Religions old and new begin to incorporate the stopped core into their narratives. Pilgrimages are made to magnetic anomalies, places where the field, though weak, still pulses due to localized iron deposits or residual crustal magnetism. These magnetic remnants become sites of spiritual significance, studied by scientists and worshipped by pilgrims alike. Meanwhile, technology accelerates to keep pace. Advances in artificial shielding, biological resistance to radiation, and atmospheric chemistry mark a new era of planetary engineering. Space travel becomes not just a dream, but a necessity. The Moon and Mars, once training grounds, are viewed as lifeboats. Not because Earth is dying, not yet, but because its stability can no longer be taken for granted. And yet, life goes on. Earth, despite its silent core, remains a vibrant world. Rain still falls. Forests still grow. The seas still cradle whales. The sun still rises. But beneath it all is a new uncertainty, a planet missing its pulse, holding its breath in the long silence of deep time. Perhaps, in some corner of the Earth, a team of scientists continues to listen to the ground, hoping to detect the faintest vibration, a whisper of renewed motion, a hint that the core, like a sleeping giant, might stir once more. But until that whisper comes, if it ever does, humanity must live on a planet where the magnetic past is a memory, and the future depends on ingenuity, adaptation, and a profound respect for the hidden forces that once kept everything in motion. In the long absence of the core rotation, Earth becomes an increasingly complex system of half-preserved balances. Each ecological and technological workaround feels less like a solution and more like a delay. The planet no longer behaves as it once did, and yet it does not collapse into sudden ruin. It simply becomes a slower, colder, and more precarious world. The population, ever inventive, adapts not to prevent disaster, but to live beside it, like one might grow used to the permanent creak of a leaning house. In major cities, radiation shielding becomes as ordinary as air conditioning. Buildings are equipped with layered polymers, smart coatings, and artificial magnetospheric domes. Even schools teach courses not just on geography or biology, but on the properties of solar wind, UVC shielding materials, and cosmic background particle trends. Children grow up knowing auroras as part of the night sky, with bedtime stories set not beneath stars, but beneath swirling curtains of magnetic green and violet. Medical fields specialize in radiological resilience. Genetic screening is employed to identify markers of UV sensitivity. Clinics distribute topical blockers and oral supplements aimed at boosting cellular repair. Cancer rates are managed through vigilant monitoring and personalized treatment regimes. Entire branches of dermatology and oncology are redefined, not as fields reacting to occasional illness, but as the front line of a new planetary norm. In agriculture, synthetic magnetism and UV filtering greenhouses become ubiquitous. Crops are grown indoors, under carefully tuned light spectra. Vertical farming, once a novelty of urban futurism, becomes the backbone of food systems. Grains, legumes, and vegetables are engineered for shorter growth cycles, denser nutrition, and higher resistance to mutagenesis. Still, yields are fragile. Pests evolve rapidly under increased radiation exposure, and without a magnetic field, certain soil microbes fail to reproduce normally, altering nutrient cycles. This forces a closer integration between farming and biotechnology. Nutrient recycling systems are integrated into irrigation lines. Soil is treated with engineered microorganisms. Drones hover over fields not to scout pests, but to deliver bursts of ionizing particle suppressants. Climate control merges with crop control. Every farm becomes a laboratory, and every harvest a calculation between radiation level and resilience. Meanwhile, in the oceans, strange patterns begin to emerge. Thermaline circulation, sluggish and confused, rearranges itself into non-traditional loops. The Gulf Stream, weakened and wandering, begins to deliver heat in unexpected directions. The Arctic doesn't just freeze, it fluctuates. Ice sheets break unpredictably and then grow again. Subpolar currents create microclimates in places that once followed equatorial rhythms. The Southern Ocean encircles Antarctica with less intensity, causing localized warming on the continent's edge. Marine life adapts in curious ways. Species migrate far beyond their historical zones. Tropical fish show up in cold water reefs. Deep-sea creatures, once bound to nutrient flows, tied to magnetic patterns in the crust, begin drifting aimlessly. Whale songs change pitch, possibly due to alterations in how sound travels through waters now subtly affected by temperature, salinity, and perhaps even magnetic anomalies in the seabed. The consequences are slow, but monumental. Fishing industries. collapse in some regions and flourish unexpectedly in others. Conservation efforts move quickly to protect migratory species that no longer follow any clear route. Coral reefs, already under siege from acidification and warming, now face radiation-damaged symbiosis. Some adapt with genetically engineered algae, others vanish. Even Earth's orbiting satellites, vital for communication, weather monitoring, and global surveillance, become less reliable. With no magnetosphere to shield them, they require regular replacements. Low Earth orbit becomes a wasteland of failed devices and expensive attempts at radiation shielding. The space around the planet thickens with debris, increasing collision risks. International treaties are signed to develop more resilient satellite shells and to manage debris with magnetic tethers or autonomous collection drones. And still, humanity presses onward. In the field of deep Earth science, attention turns away from volcanoes and earthquakes, now fewer and less destructive, and toward the core itself. With seismic activity dampened, researchers send specialized probes deeper than ever before. Boreholes fitted with pressure-hardened instruments begin to return subtle data from depths never before explored. What they find is sobering. The outer core, once a seething ocean of liquid iron and nickel, has begun to stratify. The absence of rotation has allowed it to settle, with denser elements collecting toward the base and lighter impurities drifting upward. This layer caking slows what little residual movement remains. Without convective mixing, temperature gradients sharpen. The core becomes less a dynamic engine and more a static metallic stew. The inner core, too, begins to show signs of change. Though still solid due to extreme pressure, its temperature begins to cool. The boundaries between solid and liquid metal become more pronounced. Within the inner core, once believed to align along rotational lines, now scatter. Their orientation. This disorder reduces the coherence of what tiny magnetic pulses might remain. The inner Earth becomes more like a sleeping giant than ever before, frozen in structure but not yet extinguished in heat. This cooling has far-reaching implications. As heat from the core dwindles, the mantle contracts further. Continental plates experience tension in new and unexpected ways. Rift valleys open in stable cratons. Mountains that once rose now begin to erode without replacement. Geologists note the beginning of a new tectonic era, not of collision or spreading, but of gradual geological rest. Earth's lithosphere begins to stabilize into vast, unmoving blocks. The planet's skin grows still. The psychological impact of this quiet transformation begins to take root in culture. Artists speak of the death beneath the ground. Philosophers write of a still earth and a restless species. The metaphor of a frozen heart recurs in literature, in music, in visual art. The core, once unseen and ignored, now haunts the human imagination. Its silence is the background. Noise of 1,000 speculative documentaries and doomsday predictions. And yet, even in the silence, hope stirs. Scientific institutions across the globe unite under planetary initiatives. Projects aimed at generating artificial magnetospheres are no longer science fiction. Using massive superconducting rings, plasma tunnels, and orbiting magnetic satellites, researchers attempt to build localized zones of shielding. The early models protect small areas, city-sized or facility-sized bubbles, from cosmic radiation. These zones become test beds for future planetary engineering. Some even propose methods to reinitiate convection in the outer core. These include ambitious ideas like injecting radioactive materials using lasers to melt strategic boundaries, or creating pressure pulses to restart rotational momentum. Each project borders on the impossible, but they mark a shift from survival to revival. Meanwhile, astronomers begin searching the skies with new eyes. With Earth's field gone, Cosmic particles once filtered out now reach telescopes more easily. Paradoxically, this improves our ability to study high-energy astrophysics. Observatories detect strange neutrino patterns and gamma bursts with unprecedented clarity. In this unintended advantage, a new field of stellar forensics is born. The universe itself, it seems, is taking the place of the silent Earth, whispering secrets and frequencies we had never been able to hear before. Still, life continues its quiet evolution. Insects develop thicker exoskeletons to resist radiation. Mammals adapt with more melanin, stronger DNA repair enzymes, and shorter reproductive cycles. Human populations migrate toward equatorial zones, where artificial shields are most effective and atmospheric loss is slower. Cities become modular, movable, enclosed. The planet, in a way, has become a space station, not in orbit, but in lifestyle. The Earth is not dead. It has simply entered a new age, a quieter age, one with less internal fury, but more external vigilance. No longer powered by an inner fire, but sustained by an outer resilience. Somewhere, deep beneath it all, the core remains, not gone, just still. A memory of motion, a relic of energy. And perhaps, just perhaps, a future still waiting to spin again. Beneath the surface of Earth's adaptation lies a subtle and profound truth. Nothing is truly still, even when the forces that once shaped the world seem to have fallen silent. Though the core no longer spins, and the outer layers no longer hum with magnetic vitality. The consequences of that absence continue to ripple through the systems of the planet like echoes in a stone canyon. Geologists begin noticing a change. In Earth's moment of inertia, the way mass is distributed and how it affects the rotation of the entire planet. Although the core spin was only a fraction of the total planetary motion, its inertia helped stabilize Earth's axial wobble. Without it, even the surface rotation begins to behave erratically. Earth's axis tilts slightly more than it once did. Not a dramatic, cinematic flip, but a slow drift of degrees that, over time, changes the pattern of seasons and the position of the poles. Climatologists and cartographers now deal with a moving North Pole. Magnetic compasses, long obsolete, are now museum pieces. But even GPS systems have to adjust for the shifting parameters of the rotating crust. With every year, solar exposure in certain regions increases while others fall into extended winters. Places that once bloomed with spring in April now see snow, while deserts find themselves in the path of monsoons. Agriculture becomes nomadic. Crops are grown in greenhouses, mounted on rail systems or modular drones, shifting fields based on temperature forecasts. At the same time, Earth's inner temperature continues its descent. The loss of rotational energy has allowed deeper cooling. In the planet's core, which in turn has a cumulative effect on mantle viscosity. As the mantle thickens and grows less fluid, seismic waves begin traveling faster and with less scattering. Seismologists detect subtle increases in the clarity of deep Earth tremors. The planet is becoming more solid, more unified in its internal structure, but also less forgiving. Where faults once slipped, they now hold tension longer, making rare earthquakes more dangerous. In volcanology, the decline of activity leads to a paradox. While the frequency of eruptions plummets, the buildup of pressure in remaining active. Systems becomes harder to predict. Dormant volcanoes stay quiet longer, decades, centuries even, before finally releasing all their built-up force in spectacular, continent-altering events. One such eruption occurs beneath what was once the Pacific Ocean's ring of fire, a previously unknown. Subduction fault locks for 300 years and then tears open, triggering the largest eruption in human history. Ash blankets entire hemispheres. Global temperatures drop by nearly a full degree Celsius for the next decade. Crops fail in 5 countries. Economies buckle. The eruption is a wake-up call. While the world has been watching the sky for solar radiation, the Earth's crust has continued to store its tension in silence. Efforts to monitor and manage subterranean pressure zones accelerate. New drilling techniques are developed not for resource extraction but for pressure release. Volcanic venting becomes a managed process. Some nations build geothermal parks where energy is harvested not from natural flows, but from carefully engineered subsurface pressure release systems. These operations are part energy grid, part planetary maintenance, and part psychological assurance. But even as the planet cools and stabilizes, it doesn't stop changing. Atmospheric escape, once a theoretical long-term concern, begins to manifest in tangible ways. The loss of lighter gases, particularly hydrogen and helium, reduces the density of the upper atmosphere. Earth's sky grows darker at the edges, less blue. Sound travels marginally differently in thinning air. Air pressure in mountainous regions becomes insufficient for unassisted respiration, and entire highland cultures begin migrating to sea-level regions. Space agencies respond by reclassifying human habitability zones. The comfortable atmospheric pressure belt, where normal lung function can occur without artificial support, shrinks to a narrow band hugging the planet's midsections. Above or below these belts, oxygen masks become standard for outdoor activity. High-altitude cities like La Paz or Lhasa are gradually abandoned, turned into heritage preserves or scientific observatories. Urban architecture continues to evolve. Cities are built downwards instead of outwards. Subterranean living becomes not a futuristic dream, but a modern necessity. Shielded by layers of rock and fitted with synthetic magnetospheres underground, cities flourish with gardens lit by simulated sunlight and air purified through advanced biofilters. Life below the surface is not grim. It is efficient, sustainable, and remarkably communal. Humanity learns to live like its ancestors did during harsh glacial periods, close together, beneath the wind, and with one eye always turned upward. Above ground, life adapts in strange ways. Animals develop new behaviors to cope with the higher radiation levels and shifting seasons. Some mammals begin exhibiting seasonal fur color changes unrelated to snow, but instead in response to UV intensity. Nocturnal species flourish. Insects proliferate in regions where radiation-resistant vegetation thrives. Plants evolve thicker leaves, more reflective surfaces, and altered chlorophyll pigments that protect against solar flare-induced damage. Humans, too, change. Populations slowly shift toward greater pigmentation diversity. Darker skin becomes more common even in regions that were once cloud-covered. Genetic selection favors traits like enhanced DNA repair, tolerance to fluctuating oxygen levels, and metabolism tuned to lower ambient temperatures. These changes take centuries, but they become noticeable across generations. The human species is entering a new evolutionary chapter, one shaped not by geography or predators, but by a planet that no longer spins as it once did. Culture begins to reflect this transformation. Calendar systems are revised to accommodate unpredictable seasonal shifts. Art begins to depict life underground or beneath auroras. Literature embraces a new genre, geologic realism. Stories set in a world where the Earth itself has aged out of its youthful rage and now watches its children from a still and silent core. Spiritual beliefs shift too. The core becomes a symbol in new mythologies, a divine heart that once beat and may someday beat again. Pilgrimages are made not to mountaintops, but to deep boreholes where seismic sensors still listen for motion. In one such location, 1,000 meters below Iceland's surface, researchers detect a faint anomaly, a low-frequency resonance unlike any previously recorded. It is weak, persistent, and rhythmically regular. The data stirs the scientific community. Hypotheses multiply. Is it thermal convection reigniting? Is the stratified outer core beginning to stir again, ever so slightly? Could geothermal differentials or inner core crystallization be exerting torque on the surrounding liquid metal? Or is it merely geological settling, the planet sighing in its sleep? Whatever the answer, the possibility awakens new questions. Can the spin resume? Could the geodynamo reignite after a million years of silence? Are there processes deep within Earth that persist regardless of our assumptions? For the first time in centuries, humanity allows itself a fragile hope that the silence is not eternal. As international coalitions analyze the anomaly, the public begins to take notice. News reports, cautiously optimistic, share the discovery. Artists create simulations of the Earth's core, beginning to turn again, slowly at first, then building to a momentum that generates a flicker of magnetic field. Auroras fade from the equator and retreat to the poles in these visions. Atmospheric. Loss is slow. Cosmic particles deflect once more. It is not a promise, only a possibility, but in a world grown used to adjusting. The idea of renewal is more powerful than certainty. And so, humanity waits, adapting above and below ground, evolving, enduring, dreaming. Listening not just to the stars or the wind, but to the subtle, potential heartbeat of the planet itself. A planet no longer driven by fury, but still rich. With mystery, time passes on a quiet planet. Decades stretch into centuries. Above, the auroras still dance with steady grace, spreading ribbons of light across the sky from horizon to horizon. No longer rare, nor confined to the polar regions. What was once an occasional spectacle has become the normal fabric of night. Children born under this glowing canopy no longer remember a world where the sky was simply dark. They are not burdened by the knowledge of what has been lost, only shaped by what remains. The anomaly detected deep beneath the Icelandic crust, that subtle, rhythmic vibration at the edge of seismic instrumentation, persists. It does not grow stronger, nor does it fade. Scientists continue to debate its origin. Some argue that it is the slow settling of the Earth's inner structure, a passive echo of ancient motion. Others claim it is a signal, the early heartbeat, of a reawakening geodynamo. But there is no proof, only theory. And yet the mere suggestion that Earth's core could resume spinning again has shifted the psychological climate of the species as profoundly as the physical one. Above the surface, life is in full transition. The natural world, having endured centuries of increased radiation and magnetic instability, has entered an age of evolutionary acceleration. Mutations once considered rare now emerge with increasing frequency. Some are maladaptive and short-lived. Others bring remarkable resilience. Certain plant species develop reflective epidermal cells that scatter high-energy particles. Others produce pigments that convert radiation into heat or even energy, a form of rudimentary bioelectric photosynthesis. Insects grow denser chitin shells. Amphibians evolve to detect subtle electrical shifts in their surroundings, compensating for the loss of geomagnetic orientation. Biology becomes not just reactive, but experimental. In the oceans, adaptation is equally dramatic. Species that once depended on magnetic fields to navigate now use temperature gradients, sonar, harmonics, or even trace elements in the water column to find their way. Cephalopods demonstrate increasingly complex behavioral strategies, suggesting a potential leap in oceanic intelligence. Jellyfish with altered luminescent proteins pulse in patterns influenced by the ebb and flow of solar radiation. Life, it seems, is not just surviving. It is diversifying into unexpected niches, creating ecosystems that would have been considered alien just a few generations earlier. Humanity's technological integration with Earth's new environment continues apace. Space weather forecasting becomes as critical as traditional meteorology once was. Solar storm prediction models are refined using satellite swarms and deep space particle sensors. Entire cities temporarily shut down during extreme events, retracting sensitive systems into shielded cores and switching to protected energy reserves. Urban life pulses in harmony with the rhythms of the sun, a kind of technological photosensitivity. The great metropolises are no longer the loud, sprawling hubs of the early Anthropocene. They are quieter, denser, more vertical or subterranean. Towering above-ground architecture is reserved for hardened observatories, solar collectors, and aurora capture platforms, massive panels that convert the charged particles from solar wind into usable energy. These skynets are a new form of power infrastructure, glittering like frozen waves in the upper atmosphere and humming faintly with collected energy. The economic and political centers of Earth have also shifted. Equatorial zones, with their slower rates of atmospheric loss and more consistent shielding technologies, become population magnets. The tropics, once vulnerable to disease and overheating, are now among the most stable climates available. Megasettlements like the Equatorial Arc, a band of connected cities stretching from Africa through South America and Southeast Asia, emerge as hubs of culture and commerce. These settlements are optimized for climate resilience, solar energy efficiency, and underground living. Language, too, evolves. New terms are coined to describe realities unique to this era. Lightfall refers to solar storm events visible from the surface. Gravitide describes slow tectonic shifts observed in the thickened, still-cooling mantle. And deep glow is the faint bioluminescence some organisms now emit in response to increased radiation. The vocabulary of the species shifts too. Encompass a world shaped by forces it once barely acknowledged. Yet with all this change, the question of the core remains. The persistent vibration detected in Iceland is joined by similar signals elsewhere. A faint hum beneath the East African rift, an echo under the Tibetan plateau, microtremors near the Mariana Trench. In isolation, each is explainable: shifting density gradients, residual heat pockets, subtle mineral phase transitions. But together, they suggest something more: a pattern, not a spin. Not yet, but perhaps a stirring. The theory gaining traction among deep Earth researchers is that stratification in the outer core may be beginning to destabilize. Over centuries, lighter elements like silicon and oxygen may have migrated upward while heavier iron and nickel settled downward. This separation created an energy imbalance. And where there is imbalance, there is potential for motion. The scientists propose that the inner core's crystallization may be exerting torque, minute at first, against the fluid outer layer. With time, they believe convection could resume in localized zones. If this continues, small eddies may emerge, producing localized magnetic fields. In fact, measurements from ultrasensitive magnetometers in South America and Central Asia detect weak, fluctuating anomalies, tiny chaotic fields forming and vanishing within hours. These are not global fields, they are not directional. They are magnetism, born from within. The discovery becomes a scientific revelation, for the first time in nearly a millennium. The Earth's interior may be generating magnetic lines, not in a shielded, planet-spanning field, but in ephemeral pockets, like the first bubbles of water before a slow boil. This changes everything. International coalitions invest heavily in research stations placed directly above these anomalies. New boreholes are drilled. Superconducting sensor arrays are lowered into the crust. AI-assisted modeling predicts that, if trends continue, a weak but coherent dipole field could emerge in as little as 400 years. It would be a feeble echo of the ancient geomagnetic field, barely enough to influence a compass needle. But it would mark a planetary turning point, the restart of the dynamo. Meanwhile, cultural shifts embrace this possibility. A new global festival is established, the Day of the Heart, honoring the core and the hope of its return. Across cultures, it becomes a time for stories, songs, and symbolic reenactments of fire returning to stone. Children light lanterns. Elders recite the myth of the sleeping planet. Though grounded in science, the narrative of renewal takes on mythic tones. Not everyone embraces the optimism. Some warn that an awakening core may bring instability. Heat flow resumes, they argue. Tectonic activity could spike again. Volcanoes may reactivate. The atmosphere may be reshaped once more by a changing radiation shield. Earthquakes could return. In this view, the still Earth is a safe Earth, and reanimation is a risk. But others see in the core's motion not danger, but restoration. The magnetic field, if it strengthens, could reduce the need for heavy shielding. It could slow atmospheric escape. It could once again become the guardian Earth had relied upon for eons. Perhaps, in 1,000 years, the auroras will retreat to the poles. The compasses will align once more. High-altitude cities will be rebuilt. And the stars will be viewed not through radiation filters, but with human eyes under a natural sky. And so the world waits, still evolving, still listening. The core has not spun for centuries. The magnetic field has not protected Earth for lifetimes. But now, perhaps, something stirs. A resonance beneath the mantle, a subtle eddy in the liquid metal sea, a whisper from the planet's heart. In that whisper, there is no promise, no certainty. Only the possibility that even the deepest silence can give way to motion once more. In the long, cautious years following the first hints of internal movement, the mood on Earth teeters between reverent awe and analytical precision. Science is no longer merely reactive, it becomes anticipatory, leaning into the unknown with instruments tuned to the planet's quietest frequencies. The whisper from the deep Earth has not grown louder, but its persistence lends it credibility. Across continents, the global scientific community is now coordinated in ways no political treaty ever achieved. They are united by a planet that might be turning again from the inside out. Data flows from observatories, satellites, and subterranean boreholes. In the vacuum of deep Earth knowledge, the trickle of seismic irregularities and minor magnetic blips becomes a flood of potential meaning. New algorithms are deployed to detect subtle torsional oscillations, not full rotations, but localized, twisting waves within the outer core. These waves, researchers suggest, might be early signs of kinetic reorganization. Still far from a global spin, they hint at the system trying to remember how to move. With that memory, however faint, comes an explosion of theoretical modeling. Simulations across supercomputing networks run endless iterations. If even a fraction of the core's layers began circulating, how long would it take for a cohesive magnetic field to form? Would it be stable? Would it resemble the ancient dipolar field, or be chaotic, flickering in unpredictable directions? Some models suggest it could take 1,000 years to reach stability. Others predict sudden, turbulent reversals before any equilibrium is achieved. But nearly all models agree on one point. A spinning core will mean a changing Earth. Already, the planet has adjusted to life without a magnetic shield. Humanity has evolved with new protections, new environments, and new cultural identities built around adaptation. The underground cities are not just shelters, they are hubs of innovation. Above them, aurora farms continue capturing energy. People speak in the language of radiation, solar cycles, and gravitational quietude. The Earth, once defined by motion, has become the model of controlled stillness. Any resumption of motion introduces uncertainty into a carefully balanced world. This causes sharp debate across policy, ethics, and global planning. A question emerges that no generation has ever needed to ask before. Should humanity attempt to interfere with planetary mechanics? Some factions argue for planetary encouragement. attempts to amplify the nascent movements of the outer core. They propose injecting massive quantities of energy into specific regions of the mantle, using nuclear or geothermal stimulation. The goal is not to create motion artificially, but to accelerate what has already begun. If the dynamo wants to return, they argue, humanity should help it along. Opposition to this idea is immediate and fierce. Detractors argue that any attempt to interfere with the core could destabilize the system permanently. A miscalculated energy injection might trigger mantle plumes, destabilize the crust, or even halt the slow motions currently observed. The planet has survived centuries of transformation. Better, they argue, to observe and adapt than to risk irreversible damage. In the midst of this debate, Earth's natural systems continue their slow, deliberate metamorphosis. The biosphere, which has long been seen as a victim of cosmic radiation, begins to exhibit unexpected responses. Trees grown in radiation-exposed zones produce wood with altered microstructures, denser, more fibrous, and highly resistant to fungal decay. Some of these traits, when studied at the genetic level, show signs of accelerated adaptive radiation. Natural selection, fed by a steady stream of mutations, is producing outcomes that would normally take millions of years. Similarly, human physiology continues to shift. Populations exposed to higher radiation levels for multiple generations show subtle but measurable changes. Increased basal melanin levels, faster cellular regeneration, reduced sensitivity to high altitude, hypoxia. These traits are not universal, but their presence sparks discussions on the emergence of a new human subspecies, not separate, but divergent. Homo sapiens stellaris. Some suggest a human shaped by a post-magnetic Earth and the sky's relentless exposure. And then, the unexpected happens. For the first time in nearly 1,000 years, a coherent magnetic signal is detected. Not a patch, not a pulse, but a faint, planet-wide dipolar field. Weak enough to be disrupted by any large solar storm, yet stable across several rotations. It originates from within the core, confirmed by triangulated seismic electromagnetic data. The signal is too weak to deflect high-energy particles or restore navigational reliability, but its pattern mimics the ancient geomagnetic signature. The announcement sends a global wave of wonder, disbelief, and cautious celebration. The term georesurgence enters common language. News broadcasts pause programming to display the real-time signature. It becomes a symbol, not just of Earth's changing condition, but of resilience. A reminder that the planet is not static, nor is it defeated. Beneath its cooling mantle, something has remembered how to move. It is not a full return to the past. The auroras still remain. Atmospheric escape continues, albeit at a slower rate. Radiation protocols remain unchanged. But satellites begin to show marginal improvements in longevity. High-altitude particle detectors measure slightly reduced cosmic influx. These changes are small, but statistically significant. The field, though newborn and faint, is doing work. This new era brings with it philosophical reflection. If the Earth can remember motion after centuries of silence, what other planetary systems may hide regenerative secrets? Could Mars, with its frozen core, reawaken under the right conditions? Could artificial magnetic fields developed on Earth now assist other worlds in finding their motion? A wave of exoplanetary optimism spreads across space agencies. Missions once focused on data collection shift toward experimentation. Could humanity help reignite another world's heart? Back home, governments restructure funding toward planetary sciences and deep Earth research. Boreholes become sacred in a way. Modern shrines not to superstition, but to curiosity. Children are taught to read the magnetic signals of their planet as readily as they once read stars. Cartography once again includes magnetic declination. Compass technology is reintroduced in redesigned form, not as a necessity, but as a cultural bridge, a gesture to the past. Not everyone celebrates. Some view the returning field with suspicion. They fear instability. What if it strengthens too quickly? What if it reverses? The past holds evidence of geomagnetic flips, events where north and south changed places, sometimes with chaotic transition periods. Could such a reversal now, amid a society so reliant on fragile equilibrium, cause unintended collapse? To answer this, historical studies of Earth's magnetic past are revived. Core samples from ancient lava flows, frozen with the direction of Earth's magnetism at the time of eruption, are examined with new urgency. These studies reveal that magnetic reversals were often chaotic, but survivable. The field never fully disappeared. It wobbled, weakened, split, and then realigned. Life, even in those ancient ages, adapted. Perhaps it will again. As the field grows, slowly, steadily, the decision is made not to interfere. The early debates about stimulation are resolved by inaction. Humanity will monitor, it will learn, but it will not push. The motion is the planet's alone. A truth reaffirmed. The Earth does not belong to its inhabitants. They are passengers, observers, companions. And so the Earth turns, not just in space, but within itself, slowly, quietly. A liquid sea beneath solid rock, whispering motion across thousands of kilometers. The heartbeat, once silent, is returning. Not a thunderous drum, but a soft, persistent thrum, the sound of a planet remembering its pulse. There is a new serenity in the world, not born of peace, but of understanding. The quiet resumption of Earth's internal spin is not a triumphant crescendo, but a long exhale, like the planet itself has begun breathing again after 1,000 years of suspended animation. No one alive today remembers what it was like to live under the protective dome of a strong geomagnetic field. But now, for the first time in 100 generations, humanity glimpses the possibility of returning to that invisible sanctuary. The magnetic field remains fragile, like a spider's web stretched across a storm. Yet each day it endures adds weight to the idea that it is not merely a transient glitch. Magnetic flux patterns begin to stabilize. Scientists confirm that the field now has a rough dipole shape, a magnetic north and south, although still not strong enough to fully deflect solar wind or trap charged particles in neat belts around the equator. Nevertheless, satellite systems operating in low Earth orbit report fewer malfunctions. Ground-based observatories measure tiny but significant reductions in high-frequency radiation during solar events. A small, consistent bubble is forming, not yet a shield, but the embryo of one. This embryonic field alters not only the data, streams, and technical projections, but the behavior of Earth's systems themselves. In the ionosphere, for instance, charged particle densities begin to shift. Radio wave propagation, which had long been distorted by intense solar interference, becomes slightly more stable. Long-range communication systems, once relegated to subterranean or fiber optic channels, now test partial returns to atmospheric transmission. These aren't full reversals of post-core adaptation, but subtle acknowledgments that the planet might be offering its help again. In the animal kingdom, new behaviors arise. Species once thought to have lost their magnetic orientation due to the field's collapse, such as migratory birds, sea turtles, and salmon, begin displaying curious, tentative responses to the returning signal. At first, their patterns are erratic, driven more by memory and instinct than precision. But over time, researchers observe that migration routes, once chaotic or completely abandoned, start aligning with historical patterns documented in pre-collapse archives. It's not that the creatures remember the way. It's that Earth is beginning to whisper directions again. Among humans, the symbolic resonance of the awakening core spreads. Literature, art, even politics become suffused with language of rebirth, In poetry, the iron heart stirs. In theater, metaphors of planetary awakening replace ancient mythologies. Music composed using geomagnetic wave data becomes a popular, experimental genre. One particularly haunting symphony uses the real-time fluctuations in the returning field to modulate strings and synths, creating a piece that changes subtly every time it is played. Beneath all this cultural reimagining, deep-rooted science blossoms into a golden age. With motion inside the core comes the return of weak but discernible patterns in seismic waves. Seismographs now pick up torsional oscillations rippling along the core mantle boundary. These are new forms of waves, not the familiar P&S waves of earthquakes, but deep, slow undulations with rhythms so gradual they take weeks to form a full cycle. Some researchers compare them to the slow spin of gas giants, where fluid dynamics occur on planetary timescales. These new measurements allow unprecedented modeling of the core's interior. The layer once considered unknowable becomes, if not visible, at least imaginable. We now understand that the outer core has begun to unmix stratification, that long static layering of elements is being eroded by motion. Convection patterns slowly reestablish, fed by residual heat and aided, perhaps by subtle gravitational nudges from the moon and sun. Liquid iron and nickel begin to flow more freely. The solid inner core, long, quiet, and crystallizing at a glacial pace, may be rotating, not rapidly, but enough to influence the new field's symmetry. With these observations comes the recognition of a new planetary chapter. The Earth is not returning to how it was, it is becoming something different. Its magnetic field is not a replica of its ancient self, but a novel configuration, shaped by centuries of stillness, human adaptation, and deep time transformation. In practical terms, humanity begins preparing for the changes this could bring. Shielding technologies, once considered vital, are reevaluated. Some infrastructure begins to phase out redundant radiation barriers. Not everywhere, the field remains too weak for complacency. But in areas where field strength has doubled over a decade, adaptations begin. Satellite designs are revised with magnetic interaction in mind. Lorbit manufacturing, a sector dormant since the era of increased cosmic ray exposure, reawakens. Engineers design spacecraft that can harness the weak geomagnetic field to assist in orbital stabilization and drag reduction. Even climate science is touched by the shift. The slight return of the magnetosphere begins altering how solar radiation enters and interacts with the atmosphere. Polar temperatures stabilize marginally. The stratosphere, once eroded and destabilized by unfiltered solar particles, begins to show slow, self-repairing trends. Ozone levels, monitored obsessively for generations, begin to climb. Not dramatically, but enough to mark a turn. Entire regions once at high risk of UV damage see measurable reductions in cancer rates, particularly among outdoor workers and agricultural communities. Meanwhile, new cultural rituals emerge. Every equinox, people across the planet gather to watch the auroras, which now migrate more visibly toward the poles as the field strengthens. These gatherings are not silent reverences, but celebratory. Fireworks beneath dancing skyfire, music echoing against magnetically charged air. What was once a warning sign of Earth's vulnerability has become a canvas of endurance. Yet, questions remain. The field is still young, unstable. It fluctuates. It is easily perturbed by solar maximums. Some scientists warn of premature confidence. If a core oscillation disrupts the fledgling field, could it collapse again? Could this be a false dawn? The data remains cautious. Models vary wildly. Predict rapid strengthening over the next 500 years. Others foresee a plateau followed by a collapse, the result of insufficient core energy to maintain long-term circulation. Most agree that human interference is unnecessary. For better or worse, the process now belongs to the planet. And humanity, in this time of tentative motion, reflects not just on its present, but its past. The age of adaptation, born in the stillness of the core, has shaped civilization as profoundly as the Iron Age or the digital era. We learn to live with radiation, to build beneath the ground, to evolve faster than any previous generation. Now, in the possible return of Earth's greatest internal force, we face not only survival, but redefinition. What does it mean to live on a planet that spins from the inside once again? What obligations come with the return of planetary protection? What stories do we tell now that the sky no longer punishes, but shelters? The Earth is not healed, but it is changing, growing not backward into what it was, but forward into what it can still become. Somewhere, miles beneath the crust, in the swirling metal dark, the core turns, not like it once did. Not yet, but enough to touch every compass, every cell, every sky. And above, the people of Earth, adapted, scarred, wiser, turn with it. There is a quiet awe in living during the return of something once thought lost to deep time. The core of Earth, once an engine silenced by geological entropy, now hums. With new motion, it is not the roaring dynamo of ancient epochs, but a tentative stirring, enough to alter particles, deflect winds, and ripple through the physics of life and weather. In this era, it is not invention that defines humanity, but the art of paying attention. The magnetic field, faint but measurable, continues its slow strengthening. Magnetometers embedded in ocean trenches and mountain observatories record increasingly coherent patterns. The magnetic poles, previously chaotic or even fragmented, begin tracing arcs toward new, stable positions. North and south, once theoretical anchors, begin asserting influence once more. Though not yet steady, their pull has grown strong enough that new compasses are sold in schools, not for navigation, but for education, to teach children how Earth is rediscovering its inner orientation. Migratory animals that once abandoned instinctual routes begin exhibiting synchronized behaviors again. Sea turtles return to ancestral nesting beaches with greater accuracy. Monarch butterflies, after centuries of disrupted migration patterns, chart their long paths across continents with more precision. Even whales, whose deep ocean navigation had become erratic in the absence of magnetic cues, now follow straighter courses across the planetary oceans. It is not a full restoration of past behavior. Many generations have passed. Evolution has rewritten instincts. But the return of geomagnetic structure has not gone unnoticed. Nature, as always, adapts. And now it is beginning to remember. Technological infrastructures evolve in parallel. Satellite orbits, previously calculated with extreme caution due to radiation exposure, are relaxed slightly. With increasing atmospheric protection, engineers can once again place instruments into mid-range altitudes that were abandoned for centuries. These altitudes offer improved communication latency, broader coverage, and renewed opportunities for Earth observation. New arrays of sensors are deployed in constellations that follow field lines, not just orbital paths, a marriage of orbital mechanics and magnetic geometry. In agriculture, vertical farms that once relied on heavy shielding begin to experiment with transparent designs. Light filters, which once needed to block harmful UV and ionizing radiation, are redesigned to balance photosynthesis with reduced risk. Plant growth rates increase, nutritional yields improve, and the costs of underground cultivation begin to decline. In places with high magnetic resurgence, notably around the equator, open field farming cautiously reemerges, a cultural transformations. Deepen the growing stability of Earth's inner movement becomes a motif in global identity. Across languages, new idioms are born, steady as the core. To spin again, iron dreams. Poets and philosophers treat the core as a metaphor, not just for planetary dynamics, but for personal renewal. Schools teach the timeline of Earth's inner journey, from the great stillness to the first flicker. To the current rise of structured spin, spiritual systems evolve in response. Some religions reinterpret ancient doctrines through the lens of a reawakening world. In others, entirely new movements arise, centered around reverence for planetary rhythms and internal forces. Core Watchers, a new order of contemplatives, make pilgrimages to seismographic stations where they meditate on the rhythms of subsurface motion. It is not worship in a traditional sense. It is something quieter, in alignment with the unseen. Meanwhile, scientists continue their work with relentless precision. The study of core behavior has matured into a discipline as sophisticated as astrophysics. Deep Earth simulation labs, buried beneath kilometers of rock and outfitted with zero radiation. Chambers run constant models of convection, stratification, breakdown, and angular momentum exchange. Using data from naturally occurring geoneutrinos, particles emitted by radioactive decay within Earth, they chart the thermodynamic health of the core. These models confirm that full recovery of the core's rotation, if uninterrupted, may still take thousands of years. But the motion now is sufficient to sustain and perhaps grow a functioning magnetic field. Already, the outer core's differential flow patterns resemble those of an active, albeit young, geodynamo. The inner core appears to be rotating, not just wobbling but turning slowly within its metallic shell, driven by heat gradients and fluid coupling. This coupling has side effects. Mantle dynamics, long dormant, show subtle signs of activity. Seismic events increase slightly in number, not catastrophic, but enough to remind the world that Earth's crust floats on something no longer still. Volcanic activity, too, ticks upward, particularly in regions with historically active zones. The Pacific and Mediterranean belts see a return of geothermal flux, and ancient calderas exhibit increased gas emissions. Scientists interpret this as the Earth's interior resuming its breath, a gentle inhalation of thermal activity rather than a violent eruption of instability. As a result, preparedness becomes key. Seismically active zones are monitored not with fear, but with reverence. Populations have lived so long with tectonic silence that the return of geological movement is met not with panic, but with caution and awe. Architecture is updated again, buildings designed to flex, absorb, and adapt to tremors. Infrastructure planners see this not as regression, but as re-entry into Earth's natural dialogue. Climatology also shifts. The increased shielding from the returning magnetic field causes slight but global-scale changes in upper atmospheric chemistry. Solar radiation no longer penetrates as deeply or disrupts the jet streams with the same ferocity. Weather patterns, once erratic, begin to stabilize. The once feared phenomenon of sudden stratospheric warming events declines in frequency. The climate does not become peaceful, but it becomes predictable, and predictability, after centuries of chaotic flux, is a kind of peace. This stabilization allows long-deserted regions to be re-evaluated. Portions of sub-Saharan Africa, inland Australia, and the American Midwest. Areas once abandoned due to extreme UV exposure or unreliable climate are reconsidered for habitation. Migration policies shift subtly as previously marginalized. Geographies regain viability. The great underground cities do not empty, but they develop sister settlements above ground. Humanity is slowly re-emerging into the sunlight. In orbit, something remarkable occurs. For the first time since the Great Stillness began, Earth's magnetosphere becomes visible to sensors aboard long-range solar probes. The faint, comet-like tail of magnetic particles trailing Earth is seen again. Not strong, not uniform, but real. Earth, once a planetary ember in the sun's constant storm, now carries a flickering torch of its own. And still, the core turns. It is not complete, not stable, not eternal, but it is motion. And motion, in the language of planetary science, is life. Humanity, after surviving through the stillness and adapting in the silence, is now learning to grow with the pulse returning beneath their feet. And through it all, a deeper truth emerges. The story of Earth's core is not just a chronicle of geology. It is a parable of resilience, a slow, grinding, molten lesson that even after stillness, even after silence, even after centuries of lost protection, the heart of a world can remember how to move. The world does not celebrate the return of the magnetic field with fireworks or declarations. Instead, it honors the moment with quiet, synchronized stillness, a moment at midnight, when every major city pauses its motion and dims its lights to look upward, to the auroras that still paint the sky in vivid green, purple, and electric blue. Though those lights have retreated slightly toward the poles, they remain a symbol not of loss, but of endurance. The night is calm, the fields are steady, and the earth is moving beneath once more. After nearly a millennium of stillness, Earth's core has not only remembered how to turn, it has resumed its duty as the unseen protector of life. The magnetic field, now detectable even by amateur devices, hums with a soft consistency. It is no longer just a signal on seismographs or magnetometers. It is a living force again, shaping weather, shielding satellites, guiding migrations, and stirring the liquid heart of the planet into complex, purposeful motion. The poles have begun stabilizing into predictable zones. Magnetic north holds within a corridor in the high Arctic, moving no more than a few kilometers annually. South does the same, clinging to the Antarctic shelf. For the first time in generations, human explorers can trust a compass again, and, for the first time in centuries, birds can find their ancient roots not through inherited guesswork, but through an active dialogue with the field beneath their wings. The field is still far from the robust engine of ancient Earth. It is roughly 1/6 the strength it once was. But it is growing. Each year, the rate of increase rises fractionally, a sign that the core's convective processes are not just active, but accelerating. Models suggest that in 4 to 6 centuries, the field may recover to half its historic power. If trends continue without disruption, a full magnetic revival could occur within 2,000 years. But even at this early stage, the effects are monumental. High-energy particles from space are being deflected more efficiently. The outer atmosphere thickens minutely, slowing the gradual loss of hydrogen and helium. Earth's thermal retention improves as the magnetosphere helps preserve the chemical integrity of the upper air. Cosmic radiation levels drop, particularly during periods of solar maximum. For the first time in living memory, the surface of the Earth begins to feel like a place of shelter rather than exposure. With this recovery comes reevaluation. Technologies developed to survive in a world without magnetic protection begin to shift. Radiation shielding becomes a backup rather than a necessity. Subsurface agriculture begins to give way to surface-based open-air cultivation in equatorial regions. Even the great underground cities that defined humanity's adaptation begin to expand upward. Spiral structures of glass and alloy rise to the surface, layered with smart coatings that now serve aesthetic rather than protective purposes. Daylight, long feared, is once again welcomed into homes and workplaces. Climate models stabilize further. With the magnetic field moderating solar influence, polar vortex behavior normalizes. Ocean currents, particularly the Great Conveyor belts that once risked stagnation, regain strength. Powered not just by salinity gradients, but by a more stable interaction between wind, wave, and temperature. Tropical cyclones decrease in frequency and increase in predictability. Coastal cities long abandoned are reconsidered, rebuilt, reimagined. Culturally, the resurgence becomes a defining theme of the new epoch. History books divide Earth's story into 3 phases: the age of motion, the long stillness, and the stirring core. The last is where humanity now resides. Documentaries, art, literature, and philosophy all reflect on this era, not as a return to the past, but as the emergence of something entirely new. Earth is no longer the planet it once was, nor is it the vulnerable sphere it became. It is something else, something wiser and more balanced. Science continues to expand its understanding of core mechanics. New sensors detect asymmetries in the spin, slight variations in rotation rate between different longitudes. These are not flaws, but signatures of a young geodynamo finding its rhythm. The inner core itself, thought to be a solid iron-nickel ball, is revealed through acoustic tomography to have complex, layered behavior, zones of different crystal alignment rotating at subtly different speeds. These inner dynamics may be the key to understanding the future of the field. Research also explores the idea of magnetic feedback loops. A small field generation in one region may reinforce or dampen motion elsewhere. The hope is that Earth's field will not only continue to strengthen, but stabilize against future collapses. Although nothing is guaranteed, early indicators suggest that the core has reached a state of sustained motion, not a brief pulse, but a rhythm that can endure. Space exploration benefits as well. With a nascent magnetosphere, the launch windows for manned missions expand. Previously, missions beyond low Earth orbit had to account for unfiltered cosmic exposure. Now, mission planners adjust calculations to include partial field protection. Even space habitats in orbit begin to include field shelters, zones that exploit Earth's growing magnetosphere for passive shielding. Ambitious plans are drafted for extended lunar stays, Martian-based construction, and deep space telescopes that once seemed implausible in a high-radiation Earth orbit. And still, the memory of stillness remains. Humanity does not forget. Every system, every policy, every structure still reflects the lessons learned in the silent centuries. Flexibility, redundancy, adaptability, these are not discarded with the return of motion. They are preserved, respected. The architecture of cities remains semi-subterranean. Medical systems still screen for radiation-linked genetic changes. Migration systems remain agile. The scars of the stillness become the scaffolding of the future. The return of the core spin, however, brings something less tangible but deeply felt hope. Not a naive optimism, but a seasoned belief that recovery is possible. That time, given enough patience, can restore even a planet's heart. That life, when given shelter, will reach upward again. And that, even in darkness, the forces that sustain life do not disappear. They merely sleep. In the final decades of this chapter, humanity gathers around a new kind of observatory. Located at the magnetic equator on a tectonically stable island, it is a station not of defense or emergency, but of celebration. Here, scientists monitor the core's rhythm like a planet-wide metronome. Visitors arrive from all over the world. They place their hands on a monument of polished metal that echoes the frequency of the deep Earth's motion, felt as a gentle vibration. It is not dramatic, it is not loud, but it is constant. They close their eyes, and they feel the pulse of a living world beneath them. Thank you for watching. And if you've made it this far, thank you for your curiosity and your time. We hope this story brought you a new perspective on how everything, even the very core of the Earth, can change, stop, and stir once again. We're truly sorry if this video kept you awake or made sleep a little harder. That was not the plan. But if you found peace in the pace of the science or wonder in the planet's resilience, we invite you to like this video. Subscribe to the Sleepless Scientist and share your thoughts in the comments. Tell us where in the world you are and what time it is where you're listening. Now, we invite you to let go. We'll leave you with calming sounds beneath the stars, gentle frequencies, and soft atmospheric tones to help you drift into a peaceful, grounded sleep. Good night.